If you haven't already printed out the handout, please do that now. We're going to talk about solution stoichiometry. So this is the same method basically as what we were doing with stoichiometry before, except this time we have aqueous solutions in our reactions. We're going to follow a three-step approach. We're going to find the number of moles, use our molar ratios, and if we have to use the limiting reactant, we need to do that too. Once we use our molar ratios to find number of moles, we can calculate the desired quantity. So either the mass or the concentration or the volume, whatever we want. And this is what's given on your reference sheet. I've combined all of our formulas so far. So moles is equal to mass divided by molar mass. Concentration is moles divided by volume. Moles is equal to the number of particles divided by Avogadro's number. So you can combine all of those equations through the mole. So if you know the number of moles, you can calculate pretty much any quantity. So let's take a look at the first problem. Calculate the concentration of aqueous nitrate ions when 20 grams of lead-2 nitrate is dissolved in enough water to make 100 milliliters of solution. So let's write out an equation. So we're dissolving lead-2 nitrate. It's going to dissociate into the lead-2 ions and the nitrate ions. So this is what my chemical equation would look like. And I'm dealing with grams, so a mass, but I'm also dealing with milliliters, a volume. So when I set up my stoichiometry grid, I'm going to include volume and concentration, as well as what I'm used to doing, mass, molar mass, and number of moles. So I start by filling in what I know. I'm told I have 20 grams of lead-2 nitrate. I'm asked to find the concentration of aqueous nitrate ions here. So I don't really need to worry about amounts in this lead ion column. But I'm told the volume of my solution is 100 milliliters. I changed it to liters just to make my calculations easier. So the process I'm going to go through is use my mass of lead nitrate to figure out the number of moles, use my stoichiometry to find moles of nitrate ions, and then use my C equals N over V to calculate the concentration of nitrate ions. So I use my periodic table to find the molar mass of lead nitrate. It's 331.22 grams per mole. And then moles is equal to mass divided by molar mass, which is 0.0604 moles. Now I look at my balanced chemical equation. The ratio of lead nitrate to nitrate ions is 1 to 2. So there's going to be twice as many moles of nitrate ions, which gives me 0.121 moles of nitrate ions. Now I want to calculate the concentration, so concentration is moles divided by volume. So I'm going to take my moles divided by the volume, and I get a final answer of 1.21 moles per liter. So the method is pretty much the same as what we did before with stoichiometry. The only difference really is that we have concentrations and volumes involved. So if we look at our second example, calculate the concentration of aqueous acetate ions, so that's an acetate ion, if 58.6 grams of aluminum acetate is dissolved in enough water to make 250 milliliters of solution. So this question is pretty much the same as the one above. So I'd like you to pause the video, take some time to figure this one out, and you can check your answer. So here I've set up my equation. Aluminum acetate dissolves into aluminum ions and acetate ions. I'm given the mass of aluminum acetate, so I can figure out the number of moles. There's a 1:3 ratio, so there's 3 times as many moles of acetate ions. Number of moles divided by volume gets me my molar concentration, 3.44 moles per liter. So let's try the next one. Calculate the volume of 1.85 moles per liter solution of potassium phosphate that contains 0.500 moles of aqueous potassium ions. So here we have the concentration, the number of moles, and we need the volume. So here's my equation. I have potassium phosphate dissolving in its ions, the potassium ion, the phosphate ion. And I don't have any mass values in my question, so I don't really need to have that part in my stoichiometry grid. All I need is concentration, volume, and number of moles. So this is the information that I'm given. I'm told there's 0.500 moles of potassium ions, and I'm told the concentration of potassium phosphate is 1.85 moles per liter. So if I want to know the volume of potassium phosphate, I need to know the number of moles. Well, I can use my stoichiometry. There's a 3:1 ratio of potassium ions to potassium phosphate. So I'm going to divide by 3 to get number of moles of potassium phosphate. So that's 0.167 moles. And now I'm tasked with finding the volume. Well, I have concentration and I have number of moles. Just remember your little triangle, C equals N over V, so V equals N over C. So if I take number of moles, divide by concentration, I get my volume of 0.0903 liters. Now you could also write this as 90.3 milliliters, whatever your preference. So flip to the next page of the handout. Here we have a 500 milliliter water sample. It's known to contain aqueous sulfate ions. When excess barium chloride is added, 8.68 grams of barium sulfate is recovered. What was the molar concentration of aqueous sulfate ions in the water sample? So first we have to decode what is going on here. We have a water sample, it has sulfate ions in it. We're adding barium chloride, and barium sulfate is recovered. That means it's produced as a precipitate. So let's write an equation. We have sulfate ions reacting with barium ions, and barium sulfate is produced. Set up your stoichiometry grid and fill in the values that you know. So we know the mass of barium sulfate, and I also know its molar mass from my periodic table. I know the volume of sulfate ions, and I want to know its concentration. So I'm going to figure out number of moles of barium sulfate, mass divided by molar mass. It's a 1:1 ratio of barium sulfate to sulfate ions. So that will give me the number of moles of sulfate ions. And then moles divided by volume gets me concentration in moles per liter. So that gives me a final answer of 0.0744 moles per liter as my concentration of sulfate ions in the water sample. Last example, I have 10 grams of silver nitrate added to 250 milliliters of 0.3 moles per liter aqueous calcium chloride. So I have two reactants, silver nitrate and calcium chloride. And the question is, what mass of solid silver chloride is expected? So start with your reactants, silver nitrate and calcium chloride. What do you think would be produced? Well, it looks like it's set up for a double displacement reaction, so silver chloride and calcium nitrate would be our products. Now you got to figure out the chemical formulas for each of those chemicals. Make sure it's balanced. And now you can set up your stoichiometry grid. I'm dealing with mass, volume, concentration, so I include all of them in my stoichiometry grid. And the next thing is to fill in all the values that you're given. So I know the mass of silver nitrate, I know the concentration and volume for calcium chloride. When you have a question like this, where you have values for both of your reactants, you have to check for the limiting reactant. So don't forget that. So what I'm going to do is I'm going to find the number of moles of silver nitrate and the number of moles of calcium chloride, and then I have to figure out which one is my limiting reactant. So I have my number of moles, 0.0589 moles of silver nitrate and 0.0750 moles of calcium chloride. Remember, I took the number of moles and divide by the coefficient. And the one that gets me the smallest number is my limiting reactant. So it looks like silver nitrate is my limiting reactant. So if that's my limiting reactant, that's the number of moles I use to figure out the number of moles of silver chloride. Look at the coefficients, 2, 2. They're the same, so it's a 1-to-1 ratio. So that means I have 0.0589 moles of silver chloride being produced. And now, all I have to do is fill in its molar mass using my periodic table, and then do number of moles multiplied by molar mass to get my mass. So the molar mass of silver chloride is 142.23 grams per mole. So for this question, I'm going to produce 8.44 grams of silver chloride. So just remember, if you have values for both reactants, you have to determine which one's the limiting reactant. And that's the number of moles you use to find moles of your desired chemical.